Hello, my name is Constance. I work at Rafinex as a consultant and I also do customer support. And today I want to take you through a topology optimization on our Möbius platform. This is not meant to be a comprehensive review of every single feature we have, but I want to get you to a point where you can actually get going yourself and set up your own simulations and start playing. So without further ado, let's get into it. So when you want to run a simulation, you log into the platform with the login details that we gave you. You will have noticed that your login has three details: company, username, password. The company sends you to your own space. So you should see the first time you log in pretty much a blank page of this. All simulations will not have any simulations in it. You will see a username up here. This is where you sign out. You can send us an email. There is documentation. And there's a results viewer, which I'm not going to get into today, but there will be another video on that. So when you want to make a new simulation, you click the Create New Simulation button. You give it a title. You enter a description that makes sense to you, ideally. And then you hit Create New Simulation. Then you need to upload a geometry. So you can either do this by dropping a file into here or browsing your computer. The file format must be STEP. It must contain only solid bodies, so no surface bodies, no shells, no wires. The units will be assumed to be in millimeters. You should check that that's the case, but I will show you how in a few minutes. So we browse for a file. This is my file. And then you click Confirm. And while we wait for this, I will show you this part. So this part is one of the first things that we ever optimized with our GUI. It is this little piece here. So it is a camera holder that is mounted on the edge of a board, hence the name edge mount. So you will see this 90-degree angles here in the design space. The purpose of it is to watch a 3D printer, so you can remotely turn it off in case the printer messes up, so it doesn't break the head of the printer. So now we wait. So as soon as the geometry uploaded, you will see this window. Up here you can see the ID of your simulation. If you want to go to another ID, you can just change this number up here and it will take you to another ID, which is a shortcut so that you don't have to go to the all simulations window every time. You can also have multiple browser tabs open with multiple different results, so you can compare them, which is quite a nice way of working. Okay, so what do we have here? So we have our geometry uploaded. So I think I'm going to take you through the right-hand side, the controls first. So here we have an undo and redo button. We have a save button, which is disabled because we've done nothing yet. And we've got a shortcut to the user controls. So the user controls is left click and move your mouse, rotates the model, mouse wheel, zooms in and out. Holding your left mouse button and shift and moving the mouse translates the model. And those are the most important ones, really. If you have zoomed yourself into craziness, you can also go back here with zoom to fit. You can reset the view to the original view completely. You can switch between perspective and parallel view. You can show the edges of your CAD. This is quite useful when we select the sets for the boundary conditions. You can show the bounding box. So remember how I told you should check your units, so this is how you can check. So here you can see the outermost edges, so you can from that pretty much know where the origin is, and also you see the dimensions. As well as that, you can show the origin. So here's our origin in this case. Additionally, you can project the model onto the coordinate planes by clicking on the cube down here, which can also be quite handy. And we also have a section view, which in this case for this model is not that easy to operate because it's not aligned with the coordinate directions, but it can also be quite useful, especially for the results more so than the design space. All right, so on the left hand side you have the panel with all the steps involved in setting up a topology optimization. So you can start at the top and work your way down. You don't necessarily have to follow all the steps in that order, but it does mostly make sense to stick to it. So the geometry we uploaded, you can download it here. If you click on this button, it has 3 volumes, 1, 2, and see, let's reset the view here. And 3. You can see the volumes. You can rename them, which makes it easier to assign constraints and other things to it. So I'm calling this design space 1. If you ever want to do any scripting, then it's good to stick to Unix type strings here. If not, then you can have any type of string. You can have spaces and anything. So I'm calling this design space 1. This one I want to keep because it has a camera on it, so I don't want it to be optimized away. And this is the other part of the design space. Okay, then we need some sets to actually apply boundary conditions to. Oh, one more word about the geometry volume, so you can also hide these. So you can make them visible one by one, and then sometimes that is needed to assign sets which are between 2 volumes. Okay, so now that we have the volumes named, we need some sets to apply boundary conditions to. So for this it's quite handy to have the edges on, like I said. So in order to create a set, you hit the Create Set button. You will get a random color assigned. If you don't like it, you can change it here. You can rename the set to anything you want. And in order to get faces into it, you click Select Faces, you click on the face, and you confirm. So it's quite easy. Then we need another set for the wall. Select Faces, you click, you confirm, and then we need another set. For the bolt holes, we select, then we select the inside of here. So if you have a lot of faces to select for your sets, or if it's relatively fiddly to select them, like it is a bit here, you can also export colors from your CAD program. And if you export your CAD format as step AP214, then color information will be carried over, and then on the import you will actually see a colored model, and the sets should appear as well, this menu will already be pre-populated with the sets and the colors that you chose, which can make things a lot easier. So in this case it's not that bad yet, but it can be a lot of work that you don't necessarily have to do here. So we confirm. Okay, now we have sets and we named our volumes. The next thing we have to do is make a mesh. So I told you that the menu, you don't have to do it in any order, but anything you do for the geometry. So renaming volumes, creating sets, naming sets, that is all compiled into the mesh file. So you can change that after you make the mesh, but then you have to create a new mesh. So you should do these 2 steps first, be sure what you want, then you can mesh. And well, if you make a mistake, you just delete your mesh and make a new one. So you can, there's 2 ways of selecting the mesh size. You can either use the slider. So we have an adaptive mesh refinement algorithm, so you don't necessarily have to start with a really fine mesh. So I'm going to start here with a relatively coarse one, and this will give me, I mean, even if this doesn't lead to satisfying results, you can always make another topology optimization later, but the mesh refinement should also take care of refining areas where there's where it's required. So as I said, you can set it by quality, you can also set it by target element size. So be aware that this is meters, so you can have a 1 millimeter mesh here. For example, then we have this parameter here, number of elements per circle. So if you do start with a relatively coarse mesh, you want to be sure that these cylindrical holes are refined enough, because the adaptive mesh refinement will not make them better. So you should have at least 8 elements per circle, I think. If you have features like that, round features, you can even go higher. So once you're happy with this, you click Generate Mesh. And of course, everything, this GUI runs completely in a browser. So every job that is computationally expensive, like the meshing, is sent back to the cloud, to AWS. So nothing gets done on your computer. I'm running this on a laptop that is also not super powerful. And you see, now that I made the mesh, this is locked, these two panels, because you can't make changes to them anymore. Oh, and one more thing I wanted to tell you is that when the mesh is ready, it will either, if you're in the middle of the workflow, it will be shown to you right away. If you went away and came back, you can always look at it by ticking on Show Mesh, and then you can decide whether you like it, how the quality is, and remesh or keep the mesh. Now create the boundary conditions with the sets that I just created. So we have the load of the camera, the weight, it's a force. It pushes down in -z direction. I apply it to the set. And then I make another boundary condition for the constraints. So both constraints and loads are in the same panel. So you have forces, moments, pressure with a vector, acceleration, volume force, inertial relief. You also have fixed and roller boundary conditions. So I'm gonna make a wall constraint. Make this into roller. Assign it to the wall. So this means that only the normal direction to these surfaces is constrained, so it can still, the part can slide up and down. And then I make another boundary conditions for the bolts. And I will assume this is a fixed boundary condition, and I'm going to apply them inside the bolt holes. And I will only assume that these bolt holes keep the mount from sliding down the wall, so I only need to fix them in that direction. And then I'm done with the boundary conditions. Now, if at this stage you want to get a cup of coffee or do something else, or at any time you set up the model, you can save your progress, which is, you do that here. Any major step, like hitting the meshing button, will also save the model setup. But if you're in between meshing and optimization, then you have to save yourself. So there's no autosave at the moment. And now you can go away, you can refresh this, you can close it, you can come back to it, and it will have your boundary conditions saved in this case. So once we have boundary conditions, we need to assign them to a load case. Only load cases are considered for the optimization. So you can make many, many more boundary conditions here. They will not enter the topology optimization unless they are assigned to a load case. So in this case, it's very simple. We just have one load case, and we assign all the boundary conditions to it. And then that's it. Then we make a material. well, we assign a material. And we have to assign a material to every volume. We can assign different materials to different volumes, but the design space has to be made up of the same material. So I could do this, and then I could make this holder here of aluminium or something else. In this case, I'm going to assign all 3 volumes to this material. And we're done with that. And then we come to the fun part of setting up the actual optimization. So we have additional constraints which are quite useful for most optimizations. So like I said before, I want to keep this volume here where the camera sits. And for this we have a constraint which is called keep material volume. You can also name this for additional clarity. Keep camera and assign it to keep, and that means that this volume will not be touched by the topology optimization. We have a similar constraint, but for surfaces, which is called keep material thickness. In this case, I want to make sure, of course, that at the end of the topology optimization, I can still mount this camera holder to the wall. And for that, I need to make sure that these holes still exist. So I will assign a keep material thickness constraint to these holes, make them relatively thin. Just as the diameter of the washers here. And then they should still be there at the end. Now we have a few more constraints. We have symmetry, where you can assign a symmetry plane. In this case, this geometry does not have any symmetries, because you can see here these are at different levels. But if you want to make a symmetry constraint, you can choose symmetry, and then you enter a direction, which is the normal vector of your symmetry plane, and an origin, which is by default 0, 0, 0. But if your part is not centered around the origin, then it would be something else. And then we also have 2 manufacturing constraints currently implemented. One is castable. It's pretty much the same as symmetry, so you assign the normal vector of the casting plane here, and then you can also choose a draft angle. And then the last one is member size. So member size, like the name suggests, controls how thick the elements, the struts inside the optimized parts are. So you can choose, usually you would choose a maximum here, and then you can enter this in the right units. So be aware that our topology optimizer has units assigned to everything, and make sure that they're the right units. So especially when it comes to constraints like this. Also, if you want to use member size and you want to use casting, this makes the solving quite a lot more complex, so it will take more time. And with member size, you also have to make sure that the initial mesh is small enough. So if you want to use member size, then choose a mesh size that is at least twice as fine as the maximum member size you put in here. In this case, I don't need any of these constraints. Keep volume and keep thickness are enough in this case. So now we come to the objective. So here the objective is always to maximize stiffness, so minimizing the compliance or the total strain energy. You can then choose the target volume. So in this case I'm choosing 30%. It will give you an estimated mass if you already put in the material here. You can set this by fraction of the total volume, by fraction of the design space, or by absolute volume, if you know your numbers. And then we come to the optimization. So here you need to select the load cases that you want to be considered for the topology optimization. So you don't have to run the topology optimization with all the load cases. Then you don't usually need to change the iterations unless you have issues with the convergence. So the number, of course, you can change this if you have more than one load case. But in this case, we don't. So I can leave it at 1. And like I said, we have automatic mesh refinement. By default, this is on. There are 2 parameters that guide this mesh refinement. One is the node increase factor, which is basically telling the optimizer to stop mesh refining after the number of nodes doubled in this case, or tripled if you enter 3 here. So you see the mesh here has 14,200 nodes. So this criterion will stop when the mesh reaches 28,000, about 28,000 nodes. Or you can just put in a number of refinements. So then this means it will refine 3 times and then it will stop. The refinement will stop whenever one of these criteria is reached. So whichever is reached first is the one that stops the additional refinements or the refinement steps. So then, in addition to the normal refinements, we have this high quality surface pass. And this tries to make the mesh into an isotropic mesh at the end. It's an additional refinement step. And you want to have this. This is more complex than the previous refinement, so it will take more time. So if you're just iterating very quickly, you might want to turn this off. If you want to have a part that you can send to a 3D printer, you should definitely leave it on. So once we're done with this and we're happy with all the settings, we can then hit submit. And again, this job is being sent back to the cloud. And now all you have to do is wait for the results. So there is the analysis part as well. So you don't have to, once you have your result, you don't have to leave the software to do a validation on this. You can do the validation in Möbius. Once you have your result, you can start this validation analysis here. You select the load cases you want to have validated and you hit submit here. You can also do this at the start. So when you set up a model and you want to know which load cases are, which boundary conditions are relevant, which load cases are relevant and which are not, you can reduce the complexity, or you can generally sanity check whether your model makes sense. You can run a preliminary analysis on this. So once you set up all your model, you select the load cases that you want, you hit submit. If you have more than one load case, it will split the result by load case. So it will show you results, stresses, von Mises stress, strain energy, displacements for every load case individually. And then you can also rank. You can weight your load cases accordingly before you start the topology optimization. And the same thing again, to actually check your performance of the part, of course, it's nice to have a pretty result at the end, but it's really about the performance of the parts. So in order to do that, you then run the validation analysis, which gives you all the numbers. But there will be an extra video on this because there's not really enough time to get into all of that today. So then you also have the status and the logs in the jobs panel. So every major step we had here, we have a log for. So we have one for the mesh. You can see everything that went on. Probably the most important one is the run simulation one. It takes a little bit of time to establish the connection until you can see that log. And then at the end we have the shape extraction. And then we also have the advanced panel. So the advanced panel contains 2 items which are not really related. So one is the model editor. So as everything here runs in a browser and the solver runs on the cloud, basically everything you click, every single button gets recorded in one big file that you can look at with the model editor. This allows you to script your runs, also to copy parts out individually if you want. And you can see everything that happens here. So for example, the refinement. So you can see here the options for the topology optimization: max iterations 100, mesh refinement true. We have final vertex increase 2. We have the mesh settings here. So every single thing you selected is recorded here. So it's sometimes good to know. And there are also additional options that we have not exposed in the GUI because, of course, the solver is being developed on a continuous basis and the GUI does not have all the features that the solver offers. So there are things which we don't have exposed in the GUI yet. So if there is something that you're missing, it's good to send us a mail and ask us, because the chances are that it's already there and we can add it to the input deck, even if it's not there in the GUI yet. And the other thing is import setup, which I'm going to explain to you now. So we've done our topology optimization. Now, if you want to run another topology optimization with, say, for example, 20% volume fraction here, you don't have to make a new simulation and go through the whole setup again. You can clone your ID, and that you can do here. So you can delete a simulation here. You can clone it here. So we clone. You give it a new description. And then we have a clone of the whole setup. So the sets are here, the mesh is here. We can now change the optimization setup here, the objective, to 20%. And then send it off again. Okay, so let me show you the way to have a different geometry but import the model setup. So for speed purposes, let's just clone this one so we don't have to import a new geometry. So we say this is a camera edge mount modified. So we clone it. So now we can delete all the load cases. We can delete the boundary conditions. We can delete the mesh. We can delete the constraints. We can reset this to the defaults. Okay, so now you have an empty model again. So if you want to get the model setup back that we had before, you can go to this advanced tab, import the setup. So we import it from 107. It will then import all the inputs you have made in the other model, and then you can match the sets either by name, by color, or you cannot match the sets. So let's match them by name, right? Because we have the same sets here with the same names. You can then choose what to do with sets which are not matched, and then we import. This will override any setup that is already here. Okay, so now we have to mesh again, but the mesh settings are the same. We have our boundary conditions back. We have our load case. We have our material, although it might not be assigned anymore, so you have to maybe reassign a material, but you will get a warning if you forget to do that. We have our constraints, but the constraints also need to be reassigned sometimes. Well, everything that matches a set is reassigned, but the volumes might be different, so the volumes has to be reassigned. And then, well, we're not quite ready to submit because we don't have a mesh anymore, but other than that, we will be ready to resubmit the model without clicking ourselves through the whole setup again. Okay, so let's go back to our camera edge mount. So I just want to tell you something about the log if you have to do any debugging. So it's always good to check that your preserved volume and your target volume makes sense here. So it's very easy, especially if you have the units wrong, to over-constrain this. You can also see the refined target, and then you can see the log output, which is mostly boring, but there's a few numbers which are good to check. So one is the convergence value and convergence control. These should both be at 100% after every refinement step. You can also see here the number of nodes and elements, so that is also a good thing to check. And you can see the time it took to get here. So these are mainly the numbers that would interest you. So here we can see, and also you can see, so we have steps, so these are the iterations, and we have levels. These are in bit, so these are the refines. So if we look at step on level 0, we can see where the refinement happens. So you see iteration 48 was the last one with the first initial mesh, and it converged. So that's great. It took 3 minutes, 48 seconds to get there. You can see the number of elements and nodes, and then we jump to the next iterations. Now you see the history here. It went from nothing to 1 refine, and you can see that the number of nodes and elements has increased, and since we are now with the second refine already beyond double the number of nodes, this will be the last refinement. So we will run this refinement, and then we will run the high quality surface pass, and then we're done. So you don't have to look into these logs at all if you're not interested. But if anything goes wrong, if you're not quite sure, then it is quite helpful to check. And that is really all I wanted to show you. All right, once the simulation has completed, we can come back and look at the results. So we go back into our simulation. We can hide the design space so we can see it better. And then we go to results, topology optimization, show optimized shape. And we see the optimized shape. So you can see the mesh refinement here. So you see on the preserved volume, the mesh is coarser, and on here it is finer, and here we have our preserves. And it's all looking all right. So what you get as a result is, so you can look at this optimized shape. In Möbius, you can now also fire off the validation analysis. So you click on load case 1 and submit. I'm not going to show you the results now, but this is how you do it, and then you will get the stresses, strains and displacements. What you also get is an STL of this shape, and you also get the volume mesh as a PDF, and you can download this and use this to do further post-processing in other software. If you have a dedicated solver, you can then run further analyses there and then compare it to other models or simulations you might have run. So that concludes everything I wanted to tell you today. I hope you have fun going away now and playing with the software yourself. Good luck. And if you have any problems, if there are questions that I haven't answered yet, then just send me an email. Bye.